get started. We are in solid mechanics. We have taken a diversion to solid mechanics to understand the surface forces on the right hand side of the linear momentum balance, and this first visit to solid mechanics we are discussing internal forces and stress, and in this we have discussed about the stress vector and the stress tensor. Now we are to discuss the other two topics, namely the relationship between the stress vector and the stress tensor. What is the relationship between them and what are the properties of stress tensor? Of course, you will have an example in between, numerical example in between. Okay, just to set the stage for today's discussion, we will recall this particular slide which I have seen earlier, where I summarized about stress vector, stress tensor in the reverse direction. Okay, that will set the stage for today. Okay, we said if we know these 9 components, these are the components of stress vectors acting on 3 planes parallel to the coordinate axis. So, if we know this, then we can calculate these 3 components of stress vector. Those components are along xyz axis of the stress vector. So, this is what we are going to do now, how to relate these 9 components to these 3 components. That is the first step. Second step is much more simpler, because if we know these 3 components, just use simple vector algebra to find out the components normal to the plane and tangential to the plane. Okay. This is much more simpler. The second step is much simpler. First step involves some concepts. Okay. So, we will proceed the first step now, where we are going to relate the 9 to the 3. The expression what we are going to derive is called the Cauchy's formula, named after the who derived it, namely Cauchy, whose photograph is shown here. We are going to relate stress vector and stress tensor, or to put short, 9 components to 3 components. And to have a quick idea, what you see here on the left hand side is the same slide minimized there to show that we are given those 9 components and we have to find these 3 components, which are the components of stress vector along xyz axis. Okay. Now we said that we have a plane, arbitrary plane, and then we are normal to the plane. At the point we are considering 3 planes parallel to the coordinate planes. So, now I should consider a geometry which includes all these 4 planes. Such a geometry is a tetrahedron. Okay. As you see here, I will mark minimally on this slide. So, already a lot of things are there, lot of text is there. So, if you look at ABC is the arbitrary plane whose normal is n vector here, that is shown here, okay. And the 3 planes parallel to the coordinate planes are BPC parallel to the, or whose normal is x axis, and then we have the plane CPA whose normal is y axis, and then we have the plane BPA whose normal is the z axis. Of course, all the normals are towards the negative axis, not the positive axis. Okay. So, we choose tetrahedron for this reason, that we have to relate the components of stress vector acting on this plane, we call as arbitrary plane, arbitrary because n can have any value, and to the components of stress vector acting on those 3 well defined planes. When I say well defined planes, please understand that they are parallel to the coordinate planes. Now, what else is shown here? The stress vector acting on the arbitrary plane is shown here, Tn, and then the components of the stress vector along xyz axis are also shown here in red, tau n x, tau n y, and then tau n z. Okay. This is what you have to find out. Okay. Now, what is given to us? What is given to us are the components of stress vector acting on those 3 planes. Let us consider the plane whose normal is x axis, that is the plane CPB. Okay. Now, it is a plane whose normal is towards the negative x axis, and based on our sign convention all the forces are to be directed towards the negative axis. So, that is why you see the tau xx directed towards negative x axis, tau xy towards negative y axis, tau xz towards negative z axis. Okay. We always show in terms of a positive sense. Okay. Now, similarly you have the plane A, P and then C. The components of stress vector acting on that plane are shown tau yy. Okay, let us start with tau yx. Tau yx, once again all arrows are shown in the towards the negative axis, tau yx, tau yy, tau yz. And then if you take the plane whose normal is z axis, what is that plane? A, P and B, and once again all the components are shown towards the negative axis, tau zx, tau zy and then tau zz. Whatever are shown in blue are the 9 components which are given to us. We will have to find out the components shown in red which are the components of stress vector on the arbitrary plane. Okay, what else is shown here are the areas. Delta A is the area of the arbitrary plane, delta Ax, delta Ay, delta Az which are the planes whose normals are x axis, y axis, z axis. Okay. Now, how should you imagine this tetrahedron? The way you should imagine a tetrahedron is you have a solid object, in that you have taken a small tetrahedron element. So, your tetrahedron is somewhere inside a solid object. Okay. That's how we should interpret this. Okay. Now, let us proceed further. Of course, P is a vertex of the tetrahedron. Okay. Now, we are considering the object under equilibrium. As we had discussed earlier, any part of the body is also under equilibrium. So, this tetrahedron also should be under equilibrium. So, we do a force balance and we do a force balance first along the x direction, then analogously we can write for other directions. Okay. Now, when you write a force balance, you multiply the stress values with the area on which it acts. Okay. So, we are writing a force balance x direction. So, we should account for all the components of stress vector acting along the x direction. So, let us take the component of the stress vector acting on the arbitrary plane tau nx, okay, and that is along positive axis, because when we resolve a vector along the coordinate axis they are along the positive axis. Okay. So, tau nx along the positive axis, so it is positive and the area over which it acts is delta A. Now, next coming to the x phase, tau xx is the component acting along the x direction and it is along the negative x axis. So, we have a negative sign here and multiplied by the area over which it acts, which is delta Ax. Okay. So, we expect the force balance of multiplying the stress by the corresponding area. Now, for the y phase I should consider the component which is acting along x direction, which is tau yx, okay, and then of course it is along negative x axis multiplied by the area over which it acts, it is delta Ay. Similarly, for the z direction minus tau zx into delta Az. Now, this tetrahedron will also have a body force. We will denote that body force along the x direction, along the x axis, positive x axis as Bx, and that unit of body force is body force per unit volume, and we know that the volume of tetrahedron is 1/3 delta A h, where h is the perpendicular distance from P to the surface of the arbitrary plane. So, this is the volume of the tetrahedron multiplied by the body force per unit volume. Okay. H is the perpendicular distance from P to the inclined plane, Bx body force per unit volume in x direction. Okay. Now, if you look at this expression, you have the area of the arbitrary plane and then you have the area of the planes parallel to the coordinate planes. Okay. So, now we will have to find a relationship between these two, so that you can cancel out some common factors. Okay. That is what we will do next. We are going to relate that delta Ax, delta Ay, delta Az, which are the areas of the planes parallel to the coordinate planes to the area of the arbitrary plane, which is delta A. Okay, let us do that. For that, if you look at the area of, let us say, CPB delta Ax, we can easily understand that that area is nothing but the projection of delta A on a plane whose normal is x axis. Okay. You have delta A, which is the area of the arbitrary plane. If you project on a plane on the, let us say, zy plane, you get the area delta Ax, or putting it the other way, you project on a plane whose normal is x axis. Now we will have to relate this. Okay. To relate that is what I have shown here. I have a plane which is shown this way, and then you are going to look at the area of this projected plane on this plane, okay, this arbitrary plane, and this plane for our case is the y plane, because its normal is y axis. Okay. Now if you look at the projection, then this width remains same, but this L becomes L cos theta, where theta is the angle between this plane and the horizontal plane. That is what is shown here. The actual area is L into W, the length and the multiplied with the width. If theta is the angle which it makes with the horizontal plane, then the length of the projection is L cos theta, width is of course going to remain as W. So let us write down that AP is the projected area, is W into L cos theta. W remains same, the projected length becomes L cos theta, and WL is the area of the actual plane itself, so A into cos theta. Okay, actual area of the plane is A. So the projected area is the actual area into cos theta, where theta is the angle between the plane and the in this case the horizontal plane. Okay, now how do we interpret this theta in a more general way? That is what is shown here. Okay, if you look at this triangle, which is the front view of this, front view of our, this is the arbitrary plane and this is the horizontal plane, and theta is the angle between them. Now this angle is 90 minus this angle is 90 minus theta, and hence this angle is theta. Okay. And because what does n indicate? N indicates the normal to the plane, so this angle is 90 degrees and hence this angle is theta. Okay. Now so the angle which the plane makes with the horizontal plane is equal to the angle between normal to the plane and the normal to the plane on which you are projecting. J vector is the normal to the plane on which you are projecting, n vector is the normal to your plane. So both these angles are same, angle between the plane and the horizontal plane in this case, and the angle between the normal to the plane and the normal to the plane on which you are projecting. So which means that this cos theta can be written as n dot j, n dot j. Okay, that is what I have done here. N dot j is the can be represented as cos theta. Remember, both are unit vectors. Okay. Now we can generalize this. Now of course other way of representing is shown here from a reference. So this is the plane, and what you see here is the projection of the plane. Probably would have drawn this in the engineering drawing course. Okay. Okay, so yeah, n vector, remember it's a unit vector and it has components along the I j direction, which I call them as nx, ny, nz. And now using this, what we have done is for a generic area, we will now do this for our tetrahedron. We have seen that delta x represents projection of delta A on the x plane, which means that if you apply this formula, this expression AP is equal to A into n dot j for the delta Ax, the actual area, and then multiplied by n vector dot I vector. N is the normal to the plane. Now the plane on which I am projecting is the x plane, the normal to that plane is I vector. So that is why instead of n dot j we have n dot I here, which is nothing but nx, the component of x component of the unit normal vector. Similarly for the y direction, now this becomes almost same as this. Okay, that is just same as this, delta Ay is equal to delta A n dot j, because delta Ay is the projection of our arbitrary plane on the y plane, the normal to that is j. So, n dot j is what we have to use, which is ny, and similarly delta a z is a projection of our plane on the z plane, or projection of the plane on the plane whose normal is z axis, and so we have to use n dot k giving us nz. Okay. So, now let us substitute all this in the force balance equation. We said that was our objective. We have delta a and delta ax, ay, az. We said we will relate so that we can cancel out delta a. Okay. Let us do that. These are the expressions which are seen in the last slide, relating projected area to the actual area. So, let us substitute in the force balance equation. Okay. And now delta a can be cancelled out, that was our objective. We will cancel out delta a, and then we take limit delta x, delta y, delta z tending to 0, h tends to 0. Okay. Some explanation here. First, if you look at this equation, we have cancelled out area. This is similar to what we had done earlier. When we wrote a balance for a control volume, we divided by the volume, because we wrote it for a control volume. Now we are writing over a surface, so we are dividing by the area of the surface. Second, when we derive the conservation equation, let us say for mass, left side of momentum balance, we wrote the balance of the control volume, and then we string the control volume to a point. We do exactly the same thing here as well, in the limit of delta x, delta y, delta z tending to 0, which means that we are shrinking this tetrahedron to a point, and as we have done earlier, what did we say? We string so that this aspect ratio is maintained same. We should shrink as a cube, we should not shrink as this length becoming 0 or this length very large. We should shrink symmetrically so that the shape is maintained. Similarly, here also we shrink the tetrahedron to a point, maintaining the shape of tetrahedron. So, all the delta x, delta y, delta z, the limit goes to 0, which means that h also goes to 0. What is the h? The distance between normal distance between p and the surface, that also goes to 0. And why do we do that? As always, we want always a relationship it is valid at every point in the object. Remember, we are going to substitute back, use it in the right hand side of the conservation equation. Our conservation equations are at every point in the fluid there. Now, so when we go back, we substitute a relationship which is valid at every point. So, this relationship which we are going to write now is valid at every point inside the solid object, okay. Which means that when we wrote this expression, though I did not tell you, they are just average values, exactly analogous to what we do for control volume. Remember, when we took when you took this phase, we said rho Vx is average value, rho is average value inside. Similarly, when I write tau nx is average over the arbitrary plane. When I write tau xx, it is average over this area whose normal is x axis. When we take limit, they become point values. So, conceptually they are same as what we had done earlier. Objective is to get a relationship which is valid at every point inside the solid object, okay. Fine. Now, we can do a similar force balance along the y direction and then z direction, and then get what is that we have done now. We have related this x component of our stress vector, that is what we are interested in terms of tau xx, tau yx, tau zx. If we do for y and z direction, okay, we get analogous relationship for the other two directions as well. So, now let us summarize all of them. The three relationships which we have derived, we have achieved our objective of relating the components of the stress vector to the components of stress tensor, and similarly the z direction. Okay. Now, if you observe this, if you look at the second subscript, we know that second subscript tells the direction of the force. So, that is why we have x as a second subscript, and here you have tau xx, tau yx, tau zx. In fact, that is how we wrote the balance, as we took all the components acting along the x direction. In the left hand side what you have is n, because it is a component for an arbitrary stress vector, and then that relates to, on the right hand side you have x component of the 3 different stress vectors. Okay. That is why you have x axis, y axis, z axis. Left hand side is only one stress vector acting on the arbitrary plane, right hand side you have the x components of 3 different stress vectors acting on the x, y, z plane. That is why the first subscript is x, y, z. Okay. Of course, moment you look at the second subscript, that tells you the direction in which you made the force balance. Now, what we will do is we have 3 equations. Well, let us put in a more simple way and more formal way or elegant way. Express the left hand side as a 1/3 matrix, okay, and then right hand side then can be expressed as a simple matrix multiplication of this n vector with the stress tensor. Okay. This is one row and then 3 columns. Similarly, this is also one row and then 3 columns. This is 3/3, resulting in a, of course, they are compatible. So, this 3 equations can be simply represented as a matrix multiplication of matrix of 1/3 matrix made of the components of the normal vector, and another 3/3 matrix whose components are the components of stress tensor. Okay. This is why to begin with I said, for our scope the stress tensor is almost a matrix. Okay. All the matrix multiplication rules are applicable here as well. So, how do we represent this? The stress vector, the earlier expression, this equation represents in terms of components, this equation represents in terms of a vector. Left hand side you have a stress vector acting on plane n, right hand side you have n vector dotted with the stress tensor. Okay. We are not going to discuss about dot product, formally I should say as dot product of n vector with stress tensor. Within our scope, for our understanding, you can understand that just as a matrix multiplication of n vector with stress tensor. Okay. So, this is a question we asked and you answered that. If you know the 9 components of stress tensor, okay, that is our right hand side, we can calculate the stress vector acting on any plane. When I say any plane, our n is given to us passing through that point. Remember, all are at a point. So, you should imagine you have a small point, you have a small plane and you are replacing that with 3 planes at the same point. So, that should be your imagination. 3 planes are there and you have arbitrary plane, all are very small at a point. Okay. So, if you know the 9 components of stress tensor, what are the 9 components? These are the 9 components. We can calculate stress vector, these are the 3 components of stress vector on any plane, because any plane is described by the components of the normal vector to it, and so this is a relationship which we are seeking. Okay. And also like to mention, if you look at the stress tensor, if you look at one row, what does it represent? Components of stress vector acting on x plane. If you look at one column, what does it represent? It represents x component of 3 different stress vectors. Okay. So, the way in which you have arranged nicely, when you multiply, what happens? You multiply nx with tau xx plus ny into tau yx plus nz into tau zx, and that is exactly what you have here. Okay. So, the way in which arranged it, when you multiply, you get all the components or the contribution of all the x components of 3 different stress vectors to the x component of the stress vector acting on arbitrary plane. Okay. Now, a terminology, state of stress at a point. Okay. What do we mean by state of stress at a point? This sentence is same as last sentence. If we know the 9 components of stress tensor, we can calculate the stress vector acting on any plane passing through that point, which means that at a point I can have infinite number of planes, and for any plane I can find out the stress vector acting on it, which means that whatever information is required is contained in your stress tensor. That is the advantage. That is why we came from a arbitrary plane, arbitrary axis to arbitrary plane and coordinate axis, xyz coordinate axis. That means millions of possibilities are there, infinite number of possibilities are there. By going to a stress tensor, we are limited to, we can get those values, but what needs to be given is only those 9 components. Moment I give those 9 components, I can find out 3 components for any plane. Okay. So, we are reducing infinite number of some information to just 9 components, and then of course the n vector. Okay. So, thus stress tensor has all the information to calculate the stress vector acting on any plane passing through that point. You can have infinite number of planes, you are just at a point, let us say you are at a point, you can have infinite number of planes at the same point, and just it is enough that if you have the stress tensor at that point, you can get stress vector acting on any of these planes. Okay. And hence stress tensor represents the state of stress at a point. Okay. So, of course, little bit not as easy as a vector to understand. If you look at a stress tensor, you should imagine that it tells about state of stress at a point. Why does it tell about state of stress? Because it has all the information to calculate stress vectors on any plane passing through that point. So, by this we have answered the first part of the question. Second part is of course more of vector algebra.